Okay, recording is started at this point. If you just showed up, the theme of today is maximization and minimization problems in the quant section. And it says January 16th, but let's make that today's date. Again, there were some unavoidable issues last week that led to the postponement of this session. So apologies for that. Anyway, today's theme is this: maximizing and minimizing problems, and we are ready to go here. So here is a problem. That one. Go ahead and get started on this. Remember, with multiple choice questions, please use these choices, i.e., please do not answer in the chat box. Here is a timer. Go for it. All right, ladies and gentlemen, as usual, the GMAT is a test where you are not allowed to not answer the questions. Keep that in mind. You can't not answer things on this test. So if you are stuck, you have to guess. So we have Amika, Jalaja, Janie, and Rachel without answers at this point. So please pick something that is a thing if you are one of those individuals. Okay, so let's talk about it. Again, the theme of today, Rachel, you're actually the only person without an answer at this point. So please pick something from these choices, even if it's a guess. The theme today is maximizing and minimizing stuff. And I mean, the good thing about these problems is that they can't really hide them. I mean, they've got to ask you some sort of, yeah, okay, it's a little bit weird when you first use it. That's why I tried to provide a little pictorial guide here. Wherever your name is above the other names, if you find this letter A here, you should see options A through E. The good thing about maximizing and minimizing problems, they can't really hide them. I mean, it's pretty clear when they're asking a question that it's about, what is the smallest or biggest value of something. So in this case, we want to minimize. But in general, it should be pretty clear when they are asking about maximization or minimization. So that's a good thing. I mean, unlike certain other things on this test, you don't have to dig for it. So does anybody know, like, when you are trying to maximize or minimize one quantity, does anybody know what's really the secret behind that? Like, if you're trying to maximize one quantity, what are you really trying to do with stuff in general? Yeah, right? I mean, if you think about it, like, let's say it's sort of common sense, right? Like, let's say you have a day where you really have to dedicate as much time as possible to some effort, or some activity. Like, you just need to maximize the amount of time that is available for this activity. And if you need to do that, then one thing that should be incredibly clear is that you have to minimize the time that you dedicate to all other activities of that day, right? So if you have to maximize one quantity, then the essence of the problem, like the real work of the problem, lies in minimizing other quantities. And then vice versa. If you have to minimize one quantity, then the work of the problem is really going to lie in maximizing the other quantity. So that's the deal. Any sort of thing, you probably know that. Like, if you have to, I don't know, let's say that you have some unexpected expenses and you have to pay as much as possible towards those expenses in some month. If you have to do that, then you have to minimize what you spend on everything else. I mean, this is all pretty clear. Again, when people are in testing environments, they tend to be a little bit less clear on stuff that is like that. But just think about it. It should make sense. So let's talk about it. What's the situation here? The situation here is that you have more sneakers than boots and more boots than loafers. So you have a total of 20 pairs. And then you have sneakers more than boots, which in turn you have more of than loafers. So how do you have to do this? Does anybody want to summarize in the chat box? Yeah, so RS, that's a pretty decent summary of what is the deal here. How do you have to go about doing this? Yeah, you pretty much just have to try numbers. I mean, the other thing that should be clear here is that this is a problem in which you are restricted to whole numbers. Because, you can't have 7.5 pairs of sneakers. So, and one lesson that has definitely been a thing in lots and lots of these study hall sessions is when you have a whole number restriction, algebra is just not really going to fly. So you need to, when you see a whole number restriction, when you are restricted to whole numbers, you should really be careful to think about plugging in. Your favorite method should be plugging in. And in one of two ways, depending on the problem. The first way is if it's multiple choice, you want to just try answer choices. So this problem is multiple choice. On multiple choice problems like this one, it's called back solving in our own terminology, but in other words, start from an answer choice and work backward through the information. And just see if you get a result at the end that is consistent with itself. So that's what we're going to try doing here in a second. If you get a problem that is data sufficiency, which we'll see a couple of examples of as we go, but if you get a problem that's data sufficiency, then what you want to try to do is, on data sufficiency, test cases, like list cases and test them, with the goal of trying for insufficient, with the goal of getting not sufficient. If that doesn't make sense, we'll talk about that in a little bit here when we see a data sufficiency problem. But okay, so let's try back solving. If we're going to back solve this, then where should we start in the choices? Yeah, we should actually start towards the beginning of these things. I mean, if you're saying D smiley face, that's probably a reference to the fact that D winds up being the right answer. But I mean, notice what the problem says. The problem doesn't say what is the. It says what is the least number. So if you're looking for the smallest of something that works, I mean, again, just think about how you would approach a similar type of thing in real life. Like if you want to know what is the smallest car that could tow a certain load, then you would start with really small cars and see which ones can do it. And then once something finally works, you would go ahead and just go with that one. So when you see what is the smallest, you want to start from the smallest. And when you see what is the biggest, you want to start from the biggest. Because otherwise, if you see what is the smallest, then start from the smallest choices. Because then the first one that works, it will be the smallest. The problem with starting in the middle, or especially with starting at the highest option, is that if something works out, then that doesn't mean it's the answer to the problem, because you're not just looking for the thing that works, you're looking for actually the minimum thing that works. So be careful with that. If you can, I mean, as far as eyeballing this kind of thing, you may or may not be able to do that. It depends on how much intuition you really have with these numbers. I mean, if you can look at this and see that choice A is going to be way too small, of course that's a good thing. But if not, let's just start with it. So let's just make a table. We don't really need to make a genius table, but we need to organize this at least. So the deal is that we have sneakers, we have boots, and we have loafers. And again, it's always good to write organizational information on the table. What I'm referring to in particular is I would want to write that this is supposed to be a minimum value because you're trying to minimize the number of sneakers, which means that these two guys are maximum values. So let's say that we did, I mean, if you have the intuition about choice A, then good, but at least a couple people picked it, so let's just talk about it. So if we try choice A, then that means 5 pairs of sneakers per game. If that's true, then what's the most number of pairs of boots that you could have? Yeah, it's probably, you could have 4, and that's basically it. So, well, everything is pairs. For the person saying 10, we're not counting individual shoes of any type here. It's pairs of, everything is pairs. I mean, it's good that you're thinking about that, but you want to. Pairs, everything's pairs. So remember, you have to have more sneakers. I mean, if you want to write the inequality signs, just keep your head on straight and do it. So you have more sneakers than boots, and you have more boots than loafers. So the most boots that you can have is 4 pairs, because you have 5 pairs of sneakers, and you have to have more sneakers. And so therefore, the most pairs of loafers that you can have is 3. So this is only 12 pairs. So there's no way, it's way too small. I mean, you might also realize that if you go to choice B, then you're not really adding, because you need 8 more pairs of shoes here. And if you just inch these things up by 1 pair, it's not really going to work. So B, you can probably tell, you may be able to tell that it's not going to work. If you can't tell that, then, of course, what you should do is just plug in. You shouldn't waste your time. I mean, you should just plug in B and see what happens. So you may be able to tell it's still too small. If we try choice C, then that's 7 pairs of sneakers, which means the most number of boots would be 6 pairs. And the most number of loafers would be 5 pairs. So this is a max of 18 pairs. Still not good enough. At this point, you may also be noticing the pattern that you're increasing the total pairs by 3 every time. If you see that, then you're done, of course. But if not, you just don't waste your time. 8 pairs of sneakers means 7 pairs of boots, which means 6 pairs of loafers. And so that means you can get a maximum of 21 pairs. That's not 20 pairs, but the point is that you can, of course, have fewer pairs of these things. Like if you had, so therefore, if you had, for example, 8, 7, and 5, then you'd have 20 pairs. So it's basically, that's how this thing works for the most part. Are there any questions about this approach? If you have questions, go ahead and throw them in the box. If not, let's talk about, I mean, this doesn't usually happen if you have any problem about whole numbers. So here's the same problem on your slide. If you have a problem about whole numbers, then in most cases you're going to have to plug values, like we just got done doing. So in problems about whole numbers, you are just about always going to need to plug in values. You'll almost always have to do some sort of plugging, so to speak, which means either back solving if it's a multiple choice question or testing data sufficiency cases. But if there is a firm mathematical relationship, then algebra may work. I mean, see, the problem with most problems involving maximization and minimization is that there's not really any sort of easy way to write things in terms of math. But in this problem, there actually sort of is. Because remember that you have sneakers and then you have boots, and then you have loafers, and you're trying to minimize the number of sneakers, and you're trying to maximize the numbers of boots and loafers. So let's say that I said I had X numbers of pairs of sneakers. I mean, then you might realize what the deal is. I mean, what if I have X pairs of sneakers, then what is the maximum numbers of pairs of boots that I can have? Yeah, it's going to be the next, because I mean, these have to be whole numbers. So you basically want the next whole number. You want the next smaller whole number. So in order to maximize these two quantities, I just need to make them the next two whole numbers down. So this is going to be X minus 1 pairs, and this is going to be X, sorry, technical issues there. This is going to be X minus 1 pairs, and this is going to be X minus 2 pairs. Again, you can't always do this, and you shouldn't count on being able to do it, but it certainly does work here. So the total pairs that you need is going to be the sum of these things, X plus X minus 1 plus X minus 2, which is 3X minus 3. So now the deal is you want this, I mean, this needs to be able to be at least 20. So 3X minus 3 has to be 20 or more. I mean, the deal with this inequality side is that if you can get more than 20 pairs, of course, you can just start taking away pairs of shoes and get 20. So if you solve this as an inequality, then you get 3X is greater than or equal to 23. So X is greater than or equal to 7 2/3. So 7 2/3. I mean, you can't have 7 2/3 pairs of something very clearly. So that means that 8 is the smallest value that's going to work. And as usual, when you go back and review a problem, like when you are studying problems for review purposes, you should go back and try to find as many ways as you possibly can of solving them. So if you did this by plugging cases, then you should turn around and go back and try algebra. If you did this problem with algebra, you should turn around and try plugging cases, and so on. Any questions? Okay, looks like a couple people are typing. So I'll wait a second to see what exactly you are typing. What about max for sneakers? Well, the maximum number of pairs of sneakers would theoretically be 20 pairs if you have a total of 20. Because, I mean, if your sneakers are the one you have the most of, so there's no reason why you couldn't just have all sneakers. If you were 19 1 and 1 would actually be 21. But I mean 19 1 and 1 would actually be wrong for two reasons. The first is that it doesn't add up to 20. And the second is that these need to be strict inequalities. So if these were 1 and 1, they're not on you. So I guess you would actually have to have not 20. So the maximum, if you wanted to maximize the sneakers, then that wouldn't be, because you do have to have more of each. So then you could have S's 19 pairs, I'm supposed to say 19. You could have 19 pairs of sneakers, and then you could have 1 pair of boots, and you could have no loafers. Because there's nothing in this problem that prohibits something from being 0 pairs. So, because like if you say all of these things are either this, or that doesn't mean you have all three of them. I mean, it is perfectly possible that you would have none of one type. 18 1 and 1 still wouldn't work because you can't have one of two things. I mean, you have to have strict inequalities, and 1 is not greater than 1. So there you go. I mean, yeah, just as far as the or thing goes, like if you have 20 pairs of black socks in your drawer and that's all the socks you have, then if I ask you, are all of your socks either black or white, the answer is definitely yes. There's no question about that. So just think about it for a second. Okay, let's throw another problem up there on the board and have fun with it. Here's the problem. go for it. Remember where you find answers to multiple choice items. You find them here. So there it is. And this one, I'll give you more than 2 minutes for because it's a longer problem than average. So here is some time. Have fun. Okay, so only about 7 of you have answers right now, so go ahead and please pick something pretty soon. Okay, so the choices are there. It's a data sufficiency problem. Sorry, if that was not clear. I mean, one thing about these study halls is we do expect people to be familiar with the basic logistics of the GMAT. So if you don't really know what data sufficiency is, then, I mean, we can't provide a full bringing you up to speed on that because that would pretty much take up the whole session. So if you don't know what a data sufficiency problem is, then you're going to want to just in order to really understand what's going on in these problems, you're going to want to familiarize yourself with that. But I mean, I'll put the choices up on the board in terms of what they actually are, but if you don't know what the whole sufficient, not sufficient thing is, then if you don't know what that means, then the best advice I can give is just try to follow the discussion as best you can. And then the extremely short version is that sufficient means that you have enough information to get a single unique answer, and not sufficient means that you don't. So you'll see on the board, these are always the choices for every data sufficiency problem in the world. But in order to follow the quant study halls here, since this is always the same logistics, we don't really want to have to be bogged down with introducing it every time. And that would kind of be a little bit exasperating to our regulars here. In order to understand the quant study halls here, there's 2 things that you should do, which are, first thing is understand what sufficient and not sufficient means, like basic introduction. So just have a basic understanding of what data sufficiency is and how it works. Like, in other words, just understand what sufficient and not sufficient mean. And then also, you should memorize the answer choices, which this is not really an active task of memorization. I mean, basically, you should just absorb them after doing just a handful of practice problems. They should just kind of migrate into your head by osmosis. Like, you won't really have to put effort into memorizing the choices. So, but these are what the choices mean. They're just various combinations of whether statements are sufficient to solve the problem or not. So if you're totally new to this game, then try to just follow what goes on in this problem. And then, yeah. So what we do is we look at statement 1 first. But now, the thing you might notice is that this problem, here's the problem again. This problem doesn't explicitly mention maximum or minimum. So, there's no explicit mention of maximum and minimum, so you might be wondering what the heck is this problem doing. By the way, also here's your results from the multiple choice. No consensus at all here, and this green bar is actually not the correct answer to the problem. So there's going to be a lot of schooling going on here. There's no explicit mention of max-min, so you might be wondering what this problem is doing in this edition of the study hall. So, but the deal is this. Like, what I want you to realize is you have a whole number of restrictions. And when you have a whole number restriction, it should be clear in this problem that you're going to have to test individual cases. Like that should be absolutely clear here. Because with 7 different numbers, you're not going to be able to do algebra. But unless you really have another strong insight, like if you don't have any other strong intuition, then you may want to start by considering max and min values. I mean, because when you test cases, that is, like when you test values. This is a data sufficiency issue, because if it's multiple choice, of course, you can just throw in an answer choice and watch what it does. But in data sufficiency, you have to be more on board with like understanding how to pick cases to test. But anyway, let's read through the problem, make sure we understand what's going on. So like as with any other word problem, no math at first. You want to just read the words and make sure we understand what things are in the problem and what happens with them, like how are they related. So yeah, right. So this is a pretty good RS writes this, just because I can, just allow myself to be lazier. I'll just paste it on the board. So the point is that we have 7 whole numbers in strict order of inequality. Your timing of posting that was very nice. Thank you. Yeah, you have 4 entrees, you have 3 appetizers, and they're all in strict decreasing order. They are different integers. So 7 different whole numbers. And the sum of those whole numbers is $89. So, I mean, you want to organize this. You don't need to be, the organization factor is not genius in any way, but making 7 columns for these 7 quantities will help you a lot. But you have to understand, I mean, we have lots and lots of study halls that deal with data sufficiency. So if you're not real clear if you're not really clear on the logistics of data sufficiency, you can definitely check out loads of these archived sessions of the study hall. But the most important understanding that you need in data sufficiency is what is the goal of this whole process in the first place. So just to review that, for any data sufficiency problem, you should figure out 2 things before you even start doing work. The first thing is what specifically do sufficient and not sufficient mean. That means not just yeses and nos, not just blah, blah, blah value, but like actually specifically, what do they mean? And then that quotation mark is in the wrong place. It belongs here. And then besides that, once you realize what those mean, which of those 2 is your concrete goal? This is the biggest reason why people have issues with data sufficiency, is that they're doing what they think is work. But it's not really work because it's not oriented towards any kind of concrete objective. So let's talk about sufficient and not sufficient in this problem. So we have 7 prices. The prices are all different, so we're definitely going to have to test cases. Which one of these 7 values is the goal of the problem? I mean, we don't want all 7. And I mean, the biggest mistake you can make here is to focus on all 7. When the goal of the problem is A1. So there are plenty of other data sufficiency sessions on this idea, but if you think you're going to end up with all 7 numbers, then not only are you wrong, but you have no chance of getting the problem correct. I mean, make sure you know that. This is the thing that you are focused on, because it's this. And I mean, again, any of the data sufficiency problems and the sessions of this study hall will tell you more about this. But if your if you set a goal of finding all 7 prices, then, because the thing with data sufficiency is this, like, with multiple choice, this is going to sound not like genius at all. But in multiple choice, if you get a problem wrong, it means that you probably made a mistake somewhere along the way. I mean, that doesn't sound like much of a revelation, of course. But what I want to contrast that with is this, data sufficiency. I mean, if you get a data sufficiency wrong, you may not have made any mistakes anywhere. You might have just had the wrong goal all the way from the start. Like, if you think that you're going to find all 7 numbers in this problem, then you are already wrong before your pen even touches the paper to start doing work. Like, if your goal is, I'm going to find all the prices, you're dead. Already dead. Before you do any work, dead. You have no chance of getting this problem correct. Because focus is the point. You should actually expect to find A1 while still having some unknowns in the others. That's a big, big deal. So what does sufficient and not sufficient mean in this problem? I mean, what sufficient means what? Sufficient means you are, and then let's talk about, actually let's define not sufficient first. It's actually good practice to define not sufficient. Not sufficient is you can find 2 different values. Exactly. So not sufficient means you can actually get, many is not really the way to think about it, because once you get 2, you don't have to keep going. So, but you can successfully make A1 have 2 different values. Notice what you don't do here that a lot of people do. What you should not do is say not sufficient means I don't know or I can't solve. I mean, that's not necessarily an incorrect observation, but the problem with I don't know or I can't solve is that it's not a goal. Like, it's not something that you can try for as a thing. So, in other words, don't ever phrase not sufficient in terms of I don't know or I can't solve. Because again, those things are not, strictly speaking, they are not false, but they are useless as far as goals. I mean, just think about that for a second. Like, you can actively try to get 2 values for something. This is something that you can actually try to do. I don't know and I can't solve are not things that I can try for. Those are just random hand-waving abstractions of, despair. Sufficient means I'm stuck with 1 value, with just 1 value for A1, not for everything in the chart, but specifically for my goal, which is A1. Which one of these is the goal that you are trying for? Like, when you do the work in this chart, are you trying to get sufficient or are you trying to get not sufficient? Tell me in the chat box. Like, which one of these is the goal here? It's not both of them. Yeah, the goal is not sufficient. I mean, that's really important to understand this. It's not, you can't try for this. Like, think about what being stuck with 1 value means. If you were doing algebra, then you could try for this. Like, algebra approaches actually try for sufficient, i.e., you're actually trying to solve for a value, and if you can successfully solve for a value, then it's sufficient. But this is not an algebra approach. This is an approach of plugging in different numbers and actively trying to make something happen. And if you think about this, the thing that you're trying to make happen is 2 different values. Because, I mean, stuck with 1 value means I tried to get 2 values, and I failed. Just keep that in mind. So, I mean, I'm going to, like, mark up the chart here real quick. Not sufficient is the goal. It means I got 2 values to work separately. Sufficient means it's not the goal directly. Sufficient means I tried to get two values to work, but I failed. So just keep it in mind. Whenever you do any approach ever involving testing cases, like whenever at all ever, whenever you test cases in data sufficiency, the goal is always, always, always not sufficient. Don't forget that, because sufficient is not a thing that you can try for when you test cases. Sufficient means that you are stuck and cannot get not sufficient. Okay, so we do want separate charts for the different statements. That's not very hard to do. We can just divide this chart in half. So this will be the statement 1 part up here. And this will be the statement 2 part down here. So let's talk about why this is relevant to our whole theme of maximizing and minimizing. Well, okay. So in statement 1, this has to be $16. And that's forever and ever, amen. Meaning there's no option of changing that one. So as far as cases goes, like the first case that you plug, it has to be sort of randomly chosen, but not really randomly. Like let's talk about the first case you might pick. If you don't have any other strong clue as to how you should proceed, you might as well try to find the smallest or biggest values of stuff and then reason from there. So like from here, what's easier to come up with? The smallest values or the biggest ones? Smallest values are going to be sort of hard to come up with. Because like if you think about it for a second, the smallest values you might try to be like 1, 2, 3, 4. But if you do that, it's not going to be immediately clear what numbers those should be. Because if you make it like 1, 2, 3, 4, and 5, then you're going to be left with something that is way too big. It's going to be way bigger than 16. But the maximum values are pretty easy to do. So the max values here would just be 15, 14, 13, 12. Let's see how we're doing so far. If you add these 5 numbers up, you get, this average is 14, so that's 5 times 14. This is $70 so far. And the sum has to be $89. So you have $19 left to distribute among those last 2 columns. So one way that you could divide up those $19 would be $10 and $9. Another way that you could divide those up would be 11 and 8. Does that mean not sufficient? Oh, no, it doesn't. Because remember, you have a goal. You have a value that you're concerned with, and you don't really care at all what's in these boxes as long as it works. So forget that. It's not really a thing. Once we have a 12 in this box, what is our only goal in life? Be as specific as you can about it. The goal is see if you can be even more specific than that. I mean, we do want to change the value of A1, but specifically how? Like what's the only kind of change that you could try to make to it? Up or down? Yeah, you can only lower it because these are absolute. That's the advantage of starting with. I mean, you can't make it go up. Tough you not going to work. Because like if you think about the way we chose these values, like 16, 15, 14, 13, 12 are the maximum possible values in the world that these things can have. So this is you cannot make these 5 numbers any bigger. It's impossible. So the only way to do this would be to try to lower A1. So at this point, your only goal in life, at least for the moment, is to put a smaller number for A1. But you can't make it bigger. So now let's try this and see what happens. Well, let's see if we can get it to work. So might as well put 11. I mean, if we can get someone saying 8, but you want to take baby steps, you can. I mean, if you could get 8, then of course you can get 11, but not vice versa. So let's see if that will work. Well, if we try these, let's make these 15, 14, and 13 again. So far, this is, if you just consider these 5 numbers, that's a total of $69. What does that mean you have to do with the last? Supposedly, you have to try to do what with the last 2? You have to try to make them $20. But this is at very most 10, and at very most 9. So this is basically, in short, this is not happening. So, and if you think about it, this is the best you can do, because if you try to make this smaller than 11, this issue will be even more of an issue. And if you try to make any of these 3 numbers smaller, then that's going to also exacerbate the problem of not having enough dollars available. So this is not going to work, and there's no way that you can get 11. So you are stuck with 12. The only number that you can get in that purple box is 12. I mean, notice the key to this is starting with the maximum value. The advantage of doing this, there's 2 advantages of starting with that. The first is that it's easy to generate the maximum values. You just count down until you get to the last couple and then figure out what goes there. But then also, because that's the maximum value, like, you know that the only way you can go is to step down. Like, if you found some random values that worked here, then it would. If you found random values, the problem is you wouldn't know how to organize the process from there. You wouldn't know whether to step up or down, and you wouldn't really know how to do any of that. So this is, you're stuck with 12, so that's sufficient. That means that it's not B or C or E. Now let's talk about the other part. So, I mean, let's be lazy. Laziness is good here. What I mean by that is, if you already have work that works, there's no need to reinvent the wheel here. So, like, we already have a case upstairs that works for statement 2 as well. So we can just import that case so that we don't have to do unnecessary work. And so here's those numbers from up there. The only difference now is that the left-hand column, the most expensive entree, can be anything, and the right-hand column is restricted now to $9. Like, this, you can't change this, but now you can change the other ones. Now notice again, our only goal in life is to get something that is not $12 in the A1 column. So talk about how to do that. So how are you going to do that? Well, you might think about it. I mean, it should be clear if you think about it for a sec, that trying to go up here is going to be very onerous. Because if you try to move that number up to 13, then you're going to have to bump up all of these numbers accordingly, because they have to be in strict order of decreasing order. So that's not really going to fly unless you feel like changing all of the numbers that are here. But if you, this is 10. So I mean, if you have some room to bump this down. So let's talk about doing that. If you bump this down to $11, Again, if you're focused on your goals here, you don't need to do a lot of calculating. Like you might think you have to subtract a bunch of stuff from 89 again, but actually you don't. Because all you need to make sure is that you have the same sum that you have here. So if we take away $1 here, then what's all that we have to do somewhere? Like we knocked this down from $12 to $11. So that just means somewhere we have to do what? We have to add $1 somewhere. And if you think about it, it's pretty clear where that has to happen. I mean, we can't add $1 to these two because these are going 11, 10, 9 now. And you can't add it to 13 or 14 or 15 because then you would equal the next number up. But notice that 16 is no longer restricted. So we can raise 16 by $1. And then we can just, we know we don't even have to add numbers together anymore. We can just notice that, I mean, this is definitely going to have the same overall sum if we just keep all the other numbers the same. So just keep those the same as they are there, 15, 14, 13, 10, and 9. Then that's got to have the same sum. So we made this successfully happen with two values. We made it 12. We made it 11, so it's not sufficient. Two values, not suff, period. So overall, this is going to be A alligator. There you go. Notice that the lesson for today is that any problem involving like plugging integer cases for stuff, even if it doesn't explicitly say it, if you don't really have any better way to do it, you might just want to think about maximum and minimum, just because that's an easy entry point into the problem. Like it's a very straightforward way to start the work. If we had 92 instead of 92, off the top of my head, I don't know, because that would change a lot of the calculations. Let's see, if we had 92, then... Well, if we had $92, then statement 1 would actually be impossible. Because if you have a maximum of $16, then even if you went 16, 15, 14, 13, 12, 11, 10, that would be a total of $91. So, Alicia, that would actually be an impossible problem. If you had $91, then that would be, I mean, again, with 82, the best advice I can give you here is to try to work these situations out on your own. Like now that I mean, you can make that number all kinds of numbers and see how that works out for you. If you make it 82, it's not going to work with statement 2, though, because with statement 2, you would go, if you went 9, 10, 11, 12, 13, 14, 15, that would be a total of 7 times 12 is $84. So statement 2 can't be less than $84, and statement 1 can't be more than $91. So those two cases don't work. But you should try to just make up a number and do it at home and see what you get. I mean, like, if you want to see what happens when you put in 87 or 86 or 85, then, just do it. Like, do a similar approach and see if you can get it to work. I would guess that you would probably get A or B or E or C for any of those answers that are in there at various levels. So try it, see what happens. Okay, let's see. This problem is actually also from our CAT exam. Thanks for asking. This is actually not a GMAT prep problem, although it's very closely related to some problems that are from that source. Let's try another one. Let's look at a problem from GMAT prep. Let me cancel your answers. Second one, pull the slide up. How about this one? This problem is from the GMAT prep software. So give that a shot. You'll see it show up on your board. If it's not on your board already, it'll be there momentarily. So if any of you guys still don't see the problem in the next, I don't know, 10 or 20 seconds, probably just means there's some sort of internet issue. But your board might still be blank right now because it's a graphic file that takes a decent amount of time to load. But you'll see it soon enough. I mean, yeah, I'm not going to, I can tell when you guys can see the file. So it's starting to show up for some of you, and now most of you see it. And everybody except Amy and HNL and SS should be able to see it now. And Kubi number 2. Okay, so I think everybody can see it now. So here's the timer. I mean, again, also on these problems, like before we start, let's talk about time allotment here. How long should you give yourself to do this? Chat box. So 2 minutes is definitely the wrong answer to this. Like, if you give yourself 2 minutes to do this, let me tell you a story about what will happen. What will happen is you will not finish it. I mean, here are the responses from the class again. I mean, like, this is this weird, again, common sense, man. In testing environments, people don't really have it, and it's kind of interesting. Like, just to make my point sort of obnoxiously here, let me just cross out everybody who wrote 2 minutes. No, 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 no. I mean, what is 2 minutes? Like, what is that? That's an average time. I mean, one look at this problem should tell you that it is very obviously a longer than average problem. So, 2 minutes is an average time for a quant problem. It's not a limit. I mean, if you consider 2 minutes a limit, then the result will be that you will never finish any problems that are long. You will never finish any long problems. So, I mean, it's an average, like anything else. I mean, when it takes you an average of 30 minutes to get to work with traffic and lights and stuff, then you cannot allow yourself a maximum of 30 minutes to get to work, because then if the lights are at all bad, you won't make it. So, the flip side of this is the way, because time management at the end of the day is really just a matter of being honest with yourself about whether you're making progress. I mean, if you are lost or confused at any point, you should quit, whether it's been 20 seconds or 3 minutes. I mean, you need to just be really, really honest with yourself there. So, okay, so try this problem. I'll give you 3 minutes on the timer. But again, if you are totally lost before 3 minutes, you should quit. But 2 minute limit is a big, big mistake here. Okay, only about half of you have answers, so the next 20 seconds, I mean, it doesn't matter what day your week starts on, because your day, even if your week starts on Tuesday, you still have one of each day in your week, so it doesn't really matter. Okay, there's still a few stragglers. Janine, Tyler, Charity. Pick something. Okay. All right, let's talk about it. Charity, let's see. Tyler, you're the only person who doesn't have an answer right now, so we're going to move on. But remember, on the test that you're going to take, you can't not pick an answer. So, all right, well, this is going to be a lot like the last one, right? It's going to be, here are your answers, which are not really, again, not really a consensus anywhere, but that's what you guys picked. This is going to work a lot like the other problem in the sense that you are going to have 7 columns again. This time you're going to have columns for the days of the week, but you're pretty much going to have, so let me just paste these and then worry about them in a second. We're going to find out in this short bit here. Is B correct? Well, stay tuned. Okay, so here are, let's make 7 columns. So remember that the correct answer to the problem is by far the least important aspect of the process. I mean, if you're overly concerned with what is the answer to the problem, then learning is going to be hard for you to come by. So be aware. I mean, the correct answer is not really the point. The point is the process. So let's talk about this. Sunday, Monday, Tuesday, Wednesday. And again, it doesn't matter which day starts your week. I mean, if you want to be a weirdo and start your week on Wednesday, it won't matter, because as long as there is one Sunday, one Monday, one Tuesday, one Wednesday, one Thursday, one Friday, one Saturday in your week, then it makes no difference at all. I would start this with, I would end this week with Saturday, just because Friday and Saturday are the days that are special in the problem statement. Like, notice that Friday is the second most books and Saturday is the most books. So just so that the special values are at the end of the chart, I would start on Sunday. Like, when I calendar things in general, I usually start my weeks on Monday. But in this problem, it seems to make more sense to me to put those 2 days at the end. So this is the second highest, and this is the most. Okay, now, again, what you really, really have to do that a lot of people do not do is, what is the goal? Like, what are we actually trying to accomplish here? So let's put that from the last page. And then, okay, so there. Let's talk about what this is. So, like, what does not sufficient mean, and what does sufficient mean? As specifically as possible. So, in other words, don't stick with yeses and nos, because yes and no are not goals. Also, higher than 11 and lower than 11 are also not right. What is the opposite of low? What is the opposite of more than 11? This is an absolutely key observation. It's the opposite of more than 11 is not less than 11. It's less than or equal to 11. Like, that's important, because if the number you use is 11, then it's going to change the game fundamentally here. So just notice that, because that's key. I mean, so a yes in this question means strictly more than 11. A no in this question means not less than 11, but less than or equal to 11. So in other words, not strictly less than. That matters in some problems. I can't tell you off the top of my head if it matters here. So, and also notice greater than 11 is probably inferior to saying 12 or more. Because then when you say greater than or equal to 12, it gets the point across that 12 is the smallest value that you can pick. And so greater than 11 doesn't make that as clear, at least not to me. So greater than or equal to 12. So not sufficient means that you can get both of these to happen. So not sufficient means that you can get the number on specifically Friday. You can get the number for Friday to be 12 or more, and you can get that number to be 11 or less. This is what you want to do. Before you start doing any work, you should not be thinking about yeses and nos, because yes and no are not goals. Like, yes and no are meaningless abstractions at the end of the day, and it's going to be very hard to do this work until you know what they really mean. So don't think about yes and about no. Think about greater than or equal to 12 and less than or equal to 11. And if any of you guys have trouble with data sufficiency, it's probably because you are thinking about yeses and nos and abstractions and not thinking about concrete goals. So just keep that in mind. Sufficient means that you are stuck. In other words, again, it means that you fail to make both of these happen. You fail to make both of these happen. You're stuck with one. Okay. There. So it should be clear which one is our goal. I mean, again, we can't try to be stuck with one option. We have to try to get two options and then fail. So let's talk about it. So let's divide it up again, statement 1, statement 2. So statement 1, statement 2. Okay, last week's store sold 8 copies of the book on Thursday, and again, don't forget about these restrictions. Okay, so this means this has to be 8. Forever and ever, amen, 8. So, and then the goal is to get at least 12 and then at most 11 in that column. So, I mean, let's just try it, right? I mean, again, we know what our goal is, so let's think about mins and maxes. I mean, let's just put a 12 here. This time, the highest number is undetermined. So, to make the shortest work of this, we could just put what numbers in these 4 boxes. Like, what numbers make this an extremely easy case to consider? Again, think maxes and mins here, right? You want to make this really big. So think about, yeah, just put small numbers in there. Well, not 5, but 1, 2, 3, and 4, right? So sure, 1, 2. A lot of people are putting 5, but you can't put 5. There's only 4 numbers to fill in. So 1, 2, 3, 4, 8, 12, and then you don't even need to bother calculating this because you know it's going to be big. And as long as it's bigger than 12, you're fine. And so that means we got that, which means now our only goal in life is to get this. You can do the same thing. I mean, if you make this 11 and just keep these the same, then it should be clear this is going to still be big. Because your total is 90, right? And if you need to do the math to figure this out, then don't hesitate to do it. But if you take 1, 2, 3, 4, and 8, and then either 11 or 12 away from 90, you are going to get something that is way bigger than yeah. If you use 0 copies here, then it won't matter. If they don't strictly disallow those kinds of cases, then they will write the problem so that they are non-issues. Because that is a thing. I mean, theoretically, they could have sold 0 copies on one day, but it won't. Here, it won't matter. So, okay, let's try to make 38 copies So this is not sufficient. I mean, we got two things to happen here. So this is done. We made it happen in two ways. So it's not sufficient. Let's try it here. So if we have 38 copies on Saturday and then the other days are whatever, as long as they're in the right order. Let's say this is 12. Okay, that's only 50 books. So I think you might, a little bit of thinking should convince you that if you put 1, 2, 3, 4, blah, 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 then it's not going to fly. So let's try to put maximum values for these. Because, and again, if you don't see why, then try plugging in smaller values and see where that happens. But if nothing else, if you're confused, then just go ahead and throw in maxes or mins, right? So the biggest that Thursday can get is 11. And then the biggest that Wednesday would correspond, I mean, they don't have to be strictly in order, but you have to put them 11, 10, 9 somewhere. So if you do this, then so far we've got 8, 9, 10, 11, 12 is 50. That's 88. So we have 2 books left, and this is fine. So this works. So in fact, we're not really maximizing. We're actually maximizing just those. And then the 2 is the leftover. Okay, once we have this, what is our only goal in life? Literally the only objective of our entire lives at this point is to get what? Why am I boxing that here? The box should be here. Once we have that, the only goal is to get 11 or less. So at this point, our only goal in life is to get 11 or less. And I mean, if you think about what's going on these numbers, these numbers are kind of crammed in there. So if you can't get 11, then smaller numbers will not work either. So let's try to put 11 here. That's 49 books, but the biggest values that you can put here are 10 or less, 9 or less, 8 or less, 7 or less, and 6 or less. So if you look, Rajesh, you got to read the problem more carefully. The second greatest number of copies is sold on Friday. So if you do this, then that's 49 books, but then 59, 68, 76, 83. Oh, look, that's only 89. I mean, you can't get 90 books. This is a total of 80. Maximum total is 89. Won't work. So, and if you can probably tell, if you try to put a number smaller than 11 here, then it will just cram these numbers down even lower. So nothing less than 12 is going to work. So you are stuck with 12 or more is the only possibility. So that's sufficient. So this is overall B like boy. Notice this number totally could be like 13 or 14. I mean, that's the thing, but because that's not the point. You don't need a single number in this column. You just need to verify whether you can get both of these cases. So a 13 or a 14 or a 15 would be the same as this. Do we have, NL, not really, but honestly, adding these numbers together should not take you more than about 10 or 15 seconds. So why would you? It's not a concern. I mean, if you're going out of your way to avoid a 10-second process, then instead of thinking about how to do that, you should think about where your priorities are and adjust them accordingly. Okay, got to close it down here. If you have questions related to direct business tutoring, that sort of thing, feel free to ask. If not, we are going to put it till next time. We do have a study hall next week. We usually have these every other week, but because this was a delayed session of last time, we do also meet again a week from today on the 30th. So I'm going to go ahead and kill the recording, and good night, thank you. Good night, and good luck.